Hello everyone, and welcome to part 2 of the Linear Regression with Python lecture series. In part 2, we're going to focus on getting predictions from our model. Let's go ahead and jump right back to the notebook where we left off last time. Alright, here I am at the Jupyter notebook. Last time we were able to create our model and fit the model to the training set. Now what we want to do is grab predictions from our test set. What you can do is say predictions is equal to lm dot, and then we're going to call the predict method. And with your predict method, you just pass in an x, just the features. And in this case, we want to pass in features that the model's never seen before. So we want to pass in x underscore test, which is the testing set and just the features. Then we can go ahead and check out the predictions. And if we just look at this array of predictions, notice there's a dot 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 here. These are the predicted prices of the house. However, since we did the train test split, we know that y-test contains the correct prices of the house. And we want to know how far off are the predictions from the test prices, the actual prices. There's one quick way you can visually analyze this, which is just by doing a scatter plot. So you can say something like plt.scatter from matplotlib and compare y-test versus the predictions you just made. And if they line up something like this, you know you've done a pretty good job. It means that a perfect straight line would be perfectly correct predictions. So a little bit off this sort of straight line is actually a very good job. Let's go ahead and actually create a histogram of the distribution of our residuals. I'm going to say SNS distplot. And the residuals, remember, are the difference between the actual values, y-test, and the predicted values. So I'm going to go ahead and pass in y-test minus predictions. And we can go ahead and create a plot that looks like this. And this is going to be a histogram of the residuals. Notice here that our residuals look to be normally distributed. That's a very good sign. If you have normally distributed residuals, it means your model was a correct choice for the data. If this is not normally distributed and you have some sort of weird behavior going on, you may want to look back at your data and check to see if a linear regression model was the correct choice for the data set. Later on in the machine learning section, we'll discuss other ways to analyze the correct choice of a model. Let's go ahead and continue with regression evaluation metrics. There are 3 common evaluation metrics for regression problems. I'm going to go ahead and hop quickly to the Jupyter notebook that contains the notes for this lecture in order to explain these evaluation metrics. Alright, I'm going to go ahead and hop over to the Linear Regression with Python notebook. And like I mentioned, there's 3 regression evaluation metrics, at least the most common ones. There's the mean absolute error, which is the mean of the absolute value of the errors. There's the mean squared error, MSE, which is the mean of the squared errors. And then there's the root mean squared error, RMSE, which is the square root of the mean of the squared errors. And these are all basic variations on the difference between what you predicted and the true values. Let's go ahead and compare these metrics. MAE, which was mean absolute error, is the easiest to understand because it's just your average error. You take your error, take the absolute value of it, and average it out. MSE, mean squared error, is more popular than the mean absolute error because MSE will punish larger errors, meaning it tends to be more useful in the real world because it takes into account larger errors because it's squaring them. RMSE is even more popular than MSE because RMSE is interpretable in the y units, meaning you can directly interpret RMSME in the y units, whatever your target was. And all of these are loss functions because we want to minimize them. All of these values here is something we want to minimize. We want to minimize all these errors in order to create the best model. Let's go ahead and hop back and finish calculating out these metrics in our notebook. Okay, back to the notebook. We can calculate all of these by just saying from sklearn import metrics. And off of this metrics, you can say mean underscore absolute error And this will take in your y true and y predictions. In this case, that's y test and our predictions. And you can go ahead and print out, in this case, your mean absolute error. And similarly, you can go ahead and calculate the same thing for your mean squared error. And note, I'm just using tab to autocomplete here for y test and predictions. And the other thing you can also do is grab the root mean squared error. And you can do this easily just by using NumPy np.sqrt, one of those universal functions, and then just passing in our previous result here. Since that was the mean squared error, if we want the root mean squared error, we just pass that in, and that gets us the root mean squared error. Okay, and that brings us to a conclusion for our linear regression model. We were able to successfully take in the data, split the data into a training set and a testing set based off the features and the target. Then we were able, if we go ahead and scroll back up here, to train a linear model from scikit-learn, fit the model, check out the coefficients and the intercepts to try to learn a bit about the model, and then actually make predictions using the model and analyze our residuals, basically our error of the model based off the test set. And we can actually check out the metrics themselves. Okay, like I mentioned, you can go ahead and explore the Boston dataset that I mentioned earlier, and that's linked in your notebook, if you want to redo this analysis on a real dataset. But coming up next is going to be your exercise for your portfolio project, where we're going to give you some e-commerce data, and you'll have to create a linear regression model by following the directions in the exercise. And then afterwards, we'll go over the solutions. I hope you enjoyed your first foray into machine learning. Later on, we'll delve into real datasets from Kaggle.com and perform machine learning projects that are even more in-depth. Thanks everyone, and I'll see you at the next lecture.